On behalf of the Science Library and the Institute of Theoretical Astrophysics, it is, as always, a pleasure to welcome you all to the Rosseland Lecture. Head of the Institute, Per Lilje, will give you a brief introduction to why we want to celebrate Rosseland every year and to this year's lecturer.
Thank you. Dear all, welcome to today's Svein Rosseland Lecture. Svein Rosseland was born on the 31st of March, 1894, and he passed away on the 19th of January, 1985. After a humble beginning, he in 1920 received a fellowship to study with Niels Bohr in Copenhagen. During the next few years in Copenhagen and at Mount Wilson Observatory in California, he made several theoretical breakthroughs, applying the latest findings of modern physics to astronomical problems. Most famous is perhaps what is called the Rosseland mean opacity. In 1928, Rosseland got a chair of astronomy at the University of Oslo and the directorship of the Oslo University Observatory. With strong economic support from the Rockefeller Foundation, the Oslo University Observatory was in 1934 closed and reopened the same year in a new building at the new Blindern campus as now the Institute of Theoretical Astrophysics. Svein Rosseland retired from his professorship and from being chair of the institute in 1965. At the 100th anniversary of Rosseland's birth in 1994, we started a series of annual Rosseland Lectures to honor his memory. We have had many of the world's most famous astrophysicists giving the Rosseland Lecture. This year, we are especially lucky to be able to introduce to you Avi Loeb. Loeb is the Frank B. Baird Jr. Professor of Science at Harvard University. He serves as chair of the Harvard Astronomy Department. He's chair of the advisory committee for the Breakthrough Starshot project, which aims to launch lightweight spacecraft towards the nearest stars using a powerful laser. He's the founding director of Harvard's Black Hole Initiative, the first interdisciplinary center worldwide dedicated to the study of black holes, and he is director of the Institute for Theory and Computation within the Harvard-Smithsonian Center for Astrophysics. Among lots of responsibility, I just mentioned that he's an elected fellow of the American Academy of Arts and Sciences, of the American Physical Society, and the International Academy of Astronautics. He received his PhD in plasma physics at the Hebrew University of Jerusalem in 1986. After a couple of years working on electromagnetic propulsion in Israel, he became a long-term member of the Institute for Advanced Study in Princeton in 1988, and then assistant professor at Harvard University in 1993. There he got tenure after only a couple of years, and he became a full professor in 1997 at the age of 35. He has written more than 650 scientific papers, mostly in astrophysics, covering a large number of different topics, but probably with an emphasis on the epoch of the universe when the first stars and first galaxies came to life. However, his interests span very widely, and he has also devoted time to think about the question of the possibility of intelligent life in the universe. He's just finishing writing his 6th book, which is on this matter. Now we are extremely excited to hear Professor Avi Loeb on extraterrestrial life. Please.
Thank you very much, Per. It's a great honor for me to be here in Oslo for the first time. And a great pleasure to describe what I regard as the most fundamental question that we have in science, simply because it will have a great impact on society, as far as I can tell, in many levels, starting from philosophical, religious, to scientific, and economic, political, and so forth. And I'll try to describe to you the current status, but also our ambitions for space exploration. And generally speaking, as some of you may have noticed from my writings recently, I'm trying to advocate an approach that does not imitate the past, that is looking forward to new frontiers. And there is no better frontier than exploring the universe by traveling elsewhere or sending probes elsewhere, because our life on Earth has a limited time, and as I'll describe. And there are 2 books that I'm currently in the process of writing. One is a textbook. My primary collaborator is a postdoc of mine, Manasvi Lingam, And then there is a popular level book that I just started writing, hopefully finish it by the end of this year, which I hope you will enjoy. So the fundamental question that we have is, are we alone? And this is not the motto of a dating site. It's the question of whether there is anyone out there. Are we special? Obviously, when I saw my daughters at a young age, they thought that the world centers on them. And the way they matured is by going to the street and realizing there are other kids out there just like them. Our civilization will mature once we figure out that there are others elsewhere. Right now, a lot of people, including most of my colleagues, believe that we are special. But I believe that approach is arrogant because of the examples of the past. We thought that we are at the center of the physical universe, that the sun moves around the earth. And Galileo was put in house arrest for claiming otherwise. And we realized that we're moving around the sun is moving around the center of the Milky Way galaxy, and the Milky Way galaxy is drifting through the cosmic volume around us. And clearly there is no special significance to where we are, physically. But many scientists still believe that we are at the center of the biological universe, that we are unique and special. And despite of what Copernicus taught us about the physical universe. And the reason is that life on Earth requires some coincidences, and some people think that the Earth is very rare. But my view is different. We found recently, in recent years, many habitable planets that could potentially lead to life as we know it around other stars. And in this diagram that you see here, you see the surface temperature of the star, where the sun is right around here, and this is the Earth, as a function of the amount of starlight on the planet's surface relative to the sunlight on Earth. 100% is what Earth has. And then the habitable zone, that's the region where liquid water may exist on the surface of a planet, is dictated by how much the planet's surface is heated. So you think of the star as a furnace, and if you are too close to the furnace, water evaporates, it boils off. If you are too far away, it freezes. And so there is a habitable zone, and there are plenty of planets that we found around other stars. And life as we know it requires liquid water, and liquid water requires a warm temperature and also an atmosphere. You need an external pressure, because if you take water ice and just put it in vacuum and warm it up, it turns into gas. It doesn't go into liquid, so you need an atmosphere. And for that to be retained, for an atmosphere to be around the planet, you need the planet to be massive enough to keep it in place. And the good news is that about a quarter of all the stars that we looked at so far have a planet of the size of the Earth with roughly the surface temperature of the Earth, so that liquid water may exist on its surface and the chemistry of life as we know it would take place. And that means that you roll the dice billions of times, even within just the Milky Way galaxy alone, our own galaxy, simply because there are tens of billions of stars in the Milky Way galaxy. And in my mind, it's very likely that if you arrange for similar conditions to those on Earth, you will reproduce the outcome. So I think we are not special. And I think that people that advocate that we are rare, unique, and special are showing arrogance. And in fact, if you think about, speaking about arrogance, if you think about kings or emperors that conquered a piece of land here on Earth, now that we know that there are 10 to the power 20 other planets in the observable volume of the universe, because a quarter of all the stars have planets like the Earth, there are more planets than grains of sand on all beaches on Earth. So if you think about a king or an emperor, usually it used to be an alpha male that was very proud of himself. If you think about it, it's not very different from an ant hugging a single grain of sand on the landscape of a huge beach. That's not very impressive. So even if they conquered all land on Earth, it would be similar to a single ant hugging a grain of sand on the landscape of a huge beach. So what the sky teaches us is modesty. We should be modest. And the mistake that you see throughout human history is people being arrogant. I just cannot understand why they would do that, given the big picture. And I think the only way you can remain arrogant is by limiting your field of view. If you look at the entire field of view, you cannot stay arrogant. Not to speak about the fact that each of us lives for a finite amount of time. That's a separate matter. So, life as we know it requires a furnace, a star that would keep you warm, on a planet like the Earth that would keep an atmosphere. We have a warning sign that an atmosphere is necessary for life, and that comes from Mars. Mars doesn't have an atmosphere. It used to have an atmosphere early on, and it lost it. Partly because the magnetic field was not strong enough, partly because the solar wind perhaps stripped it off. But the main reason, its gravity is weaker than the Earth's gravity. It's about a tenth of the mass of the Earth. So that's a warning sign that you cannot we don't see any creatures crawling on the surface of Mars. You clearly need an atmosphere. Now, speaking about creatures, I mean, it's possible that life was brought to Earth from Mars because we have found rocks on Earth that came from Mars. One of them, for example, did not heat up by more than 40 degrees on the journey. So it's possible to lift rocks off the surface of a planet in a very gentle way by a process called spallation. And then this rock would fly into space, eventually penetrate through the Earth's atmosphere. Only the surface of the rock would heat up. The interior will stay relatively at the same temperature. And then even the impact would not hit the rock by more than 40 degrees. So you can imagine life being transferred. And it's possible that life started on Mars, was brought to Earth. It doesn't solve the origins of life question, because we still need to explain it on Mars. But it's possible. And there are creatures that can sustain extreme conditions. They are called tardigrades, water bears. They are microscopic. You find them in any puddle of water, when it rains, for example. And they have a mechanism for repairing their DNA. So if they're exposed to extreme temperature conditions, in fact, some of them were sent in a spacecraft to space, were dehydrated, put in vacuum, irradiated by cosmic rays and X-rays from the sun. Then they were brought back to Earth after a week, and half of them produced healthy embryos. So they have a repair mechanism that keeps their DNA intact. And it's possible to imagine such animals serving as tiny astronauts and moving from one planet to another. And speaking about multiple planets in a system, there is a dwarf star. So most of the stars in the Milky Way galaxy, and in general, are dwarf stars. They're about a tenth of the mass of the sun. And the nearest star to us is 12% of the mass of the sun. There is another low-mass star, a TRAPPIST-1, that is at about 25 light years away, and it has 7 planets found around it as they transit the face of this star. And out of those, 3 are habitable. And there are E, F, and G in this diagram. Just like the Earth in principle, and they have roughly the size of the Earth. The Earth, this is the radius of the planet as a function of its mass, and the Earth sits here. But these other planets of the TRAPPIST system are scattered around the Earth or Venus, and they are Earth-like planets. And the interesting question is whether they have an atmosphere. Do they have liquid water on their surface. And since they are densely packed, life can be transferred from one planet to another, in principle. Now, interestingly, one can ask, when is life most likely to evolve in the history of the universe? We know that life exists here on Earth right now, but there were stars forming in the universe starting from when the universe was 1% of its current age. And the stars will continue to burn for 1,000 times longer than the sun in the future. These are the dwarf stars that I mentioned before. And so the question is, in this entire history, from the first stars to the last stars, when is life most likely to exist? Why do we find ourselves right now next to a star like the sun? We could have existed in the future, we could have existed in the past, around other stars. And so, in particular, a star like TRAPPIST-1 lives for about 1,000 times longer than the sun, up to 10 trillion years. And so that's a significant factor. The sun will have a lifetime comparable to the present age of the universe. So it's not surprising that we are next to a star that has a lifetime, an age, comparable to the age of the universe right now. But it will die. The sun will die soon enough, and then the nearest stars that are much smaller in size will keep burning their nuclear fuel for 1,000 times longer. So why aren't we next to a low-mass star? And of course, the very first stars started much earlier, when the universe was around 100 million years old. And that's 1% of the present age of the universe. And so in this entire history, the question is, when did life start? Now, there is a limit to how early life could have started, because the universe as a whole was hotter at early times. The universe is expanding and cooling. We know that, we see that. So if you go back in time to when the universe was about 15 million years old, that's when it had room temperature. Right now, the universe has a very cold temperature. The cosmic radiation that fills up the universe has a temperature of about 3 degrees Kelvin, 3 degrees above absolute zero. But if you go back to when the universe was 15 million years old, much earlier, when it was 100 times smaller in terms of its expansion, then the average temperature in the universe was room temperature, like we have in this room. If there were any planets back then, potentially they didn't need a star to keep them warm. The surface would have been just at the right temperature to have liquid water. But the first stars formed afterwards, so we don't think, based on the standard model of the universe that we have, that there was any life back then. But this was the earliest time that you could have started, because if you go even farther back in time, the universe was too hot. And then if you plot the likelihood of when life is most likely to exist, that really depends on what is the maximum mass of a star that you allow yourself to be next to. If you allow yourself to be next to a star like the sun, then now is the right time. But low-mass stars live much longer, so if you allow yourself, if you allow life to exist around low-mass stars, you're more likely to exist in the future around a star like TRAPPIST-1. Why don't we find ourselves in the future around a star like TRAPPIST-1? The likelihood for that would be at least 1,000 times longer. The answer may be that these stars are different from the sun. They change a lot. And also, in order to keep yourself warm, to be in the habitable zone, you need to be closer to the star. And then the planet is more vulnerable to getting its atmosphere stripped by the wind coming from the star. So it's quite possible that we are not next to a dwarf star for a variety of reasons. There is another interesting reason, which is that the ultraviolet light from the sun is helping life on Earth. It's helping the diversity of species. And if you calculate what is the time that you have to develop many species, then you find that only stars with a mass above about 60% of the mass of the sun are capable of developing the diversity that we see on Earth and life as we know it. And presumably, the low-mass stars simply don't produce enough ultraviolet radiation. Now, in terms of searching for life, we might want to search first nearby. And so the solar system is the best place. And we all know about searches for water on Mars. Recently, there were plumes of gas, sort of like geysers, coming off Enceladus, which is a moon. These plumes of gas around the Enceladus were discovered by the Cassini mission that have flown nearby Saturn and found these plumes. And these plumes of gas indicate that under the surface ice, there is probably liquid water. And you might wonder whether there are fish down there or some other living organisms. And so one way to find out is by flying through the plumes. And we need a follow-up mission beyond Cassini to actually scoop up some material from these plumes and figure out whether there are molecules that are potentially indicative of life under the surface ice. The same is true about Europa, which has an icy surface, and there could be life in the water underneath, and the question is how to find it, perhaps by drilling through the ice, and that's a moon of Jupiter. And then there is Venus that potentially could have life in its clouds. Did you ever wonder, looking at the sky, why the clouds are white and not green? Potentially, you could have had life in the clouds on Earth. Turns out that the lifetime of any life that goes up the air is not long enough to develop green clouds because of the ultraviolet illumination by the sun. But it's a non-trivial question, actually. Why isn't there life in the clouds, on Earth? There could be life in a cloud layer on Venus, as some people calculated. And an interesting question is, if we find life in the solar system, is it the same form of life as we have on Earth? Because if it's the same, there is the possibility that it was transferred from one place to another. There is also the possibility that there is only one path for life. If we find different forms of life, then we know that there are multiple ways of producing life. That's very interesting to know. And one way we can find out is also by doing laboratory experiments. If we create synthetic life in the laboratory, we can improve our imagination, because usually what we expect elsewhere depends on what we imagine, what we have found here on Earth. And just like in the context of cosmology, we found the laws of physics in laboratory experiments and then used them to explore the universe. In the same way, we can do laboratory experiments, produce synthetic life, and improve our imagination as to where to look for life in astrophysical environments, in the sky. So that's very important. Not many people are doing laboratory experiments for producing synthetic life right now. Now, there is, of course, the possibility that it's not only primitive life out there, it's intelligent, and it might even be more intelligent than we are. We might not be the smartest kid on the block. If you look at a bunch of kids in the kindergarten, often the kid that claims that he or she are the smartest are not. And so seeing people think that way probably means that we are not. And also, another simple reason is that we started developing our technology, hundreds of years ago, and that's much less than the amount of time available. And if you catch another civilization at a random place in their evolution over billions of years, it's much more likely to find it much more advanced than we are. And of course, we will not recognize very easily the signatures from a more advanced technology, sort of like showing a caveman a cell phone. The caveman would think, oh, it's a piece of rock that is just polished a little better. And so there might be a lot of what we call natural phenomena that are not, and we haven't figured it out yet. And so here is an example. Suppose you had a bright city like Tokyo. At a distance, how far away can we detect it with our current telescopes? And here I don't really mean a city on a planet. It could be a spacecraft that has artificial light coming from it. Now, how can we tell the difference between a spacecraft emitting its own light versus all the other objects in the solar system which are reflecting sunlight? A simple way to tell is by the way that the brightness of this object changes as it moves away from us. If it reflects sunlight, the amount of sunlight intercepted by the object drops as 1 over distance squared, and then we are getting another factor of 1 over distance squared. So altogether, you get 1 over distance to the 4th power, while if the object emits its own light, it gets dimmer as 1 over distance squared as it recedes away from us. So you can tell the difference between an object emitting its own light and an object that is just reflecting sunlight. And when I asked one of the leaders in exploring the exploration of the Kuiper Belt about this, I asked him, did you ever check if the objects you're looking at are changing their brightness as 1 over distance squared or 1 over distance to the 4th? He said, why should I check? It's obvious. It must be 1 over distance to the 4th. So I think one of the issues is if you're not open to discover new things, you will never discover new things. Much of life is a self-fulfilling prophecy. And that's an important message to the young people. Don't ever downgrade your future by thinking that you're not good enough based on what other people tell you. Because if you do believe what other people tell you, you will fulfill their prophecy. You should believe in yourself irrespective, because whatever exists out there has nothing to do with popularity on Twitter. It exists out there because it's there. And so if we want to go out to the cosmic street and look at other kids, we shouldn't pay attention to what our family members are saying. That's irrelevant. They can say nonsense. There could be people reporting about unidentified flying objects that are complete nonsense. There could be people making up stories in science fiction that are complete nonsense. But that's irrelevant. What matters is what is out there. And science is all about evidence. And we should collect evidence without a prejudice, without assuming that we know the truth before we actually collect the data. And if you look at human history, a lot of the progress was delayed just because people thought that they know the answer in advance. And just one simple example, Otto Struve was an astronomer that in 1952 wrote a paper saying, oh, we see Jupiter at a certain distance from the sun, but what happens if Jupiter is closer to its host star? It would actually move the star back and forth much more, and we can potentially search for close-in Jupiters, either by monitoring the motion of the host star or by seeing a transit of the star. 1952, for 4 decades, time allocation committees on telescopes refused to give time to astronomers to search for such systems. Why? Because they said, in the solar system, Jupiter is far away. We have a good, sound theoretical understanding of why Jupiter is far away. And these are people with ties, sitting on committees, saying, we are all reasonable people. We should not waste telescope time to look for planets that are close in, just like Jupiter, but close in to their host star. It sounded reasonable. These are reasonable people. Everyone respected them. They honor each other with prizes, with societies, so forth. But they were wrong. Because when someone in the early 90s started checking, they found a lot of systems with so-called hot Jupiters, using exactly the methods that Otto Struve outlined 4 decades earlier. And that opened the entire field of exoplanets. That was the beginning of discovery of planets outside the solar system. What's the moral of the story? Committees do not determine the truth. If people are not open-minded, we're delaying our progress of knowledge. We should take risks, of course, with some moderation, but we should nevertheless allow for risk-taking. Now, turns out that in principle you can detect Tokyo at the edge of the solar system with the Hubble Space Telescope. And it's worth checking if there is something out there with artificial light. The nearest star to us is, it's actually a star system of 3 stars. It's the Alpha Centauri triple system. It has 2 stars similar to the Sun, Alpha Centauri A and B, and then the 3rd star, Proxima Centauri. And next to the nearest star, Proxima Centauri, there was a planet discovered. This star system is 4 light years away. It means that it takes light 4 years to reach us from that star system. And the same in reverse. So the elections, for example, in the United States 2 years ago, that signal did not reach. It only went halfway to that star system. They are still quite confident that we are an intelligent civilization. It turns out that Proxima Centauri hosts a habitable planet. It's called Proxima b. And that star is 12% of the mass of the Sun. It has a lifetime of trillions of years, about 1,000 times longer than the current age of the Sun. And Proxima b is 20 times closer to the star than the Earth is from the Sun. Now, the interesting question is, can we visit this planet? Can we fly by it, take a photograph of it, and see whether it has oceans on the surface, or maybe it's a desert? And I'm 57 years old, as of a couple of weeks ago. And when this project that I'll describe was conceived, I was even younger. The question is, could I get the answer in my lifetime, a photograph of this planet from close by, flyby? And to do that, you really need the spacecraft to move at 1/5 of the speed of light, so that within 20 years it will get there, and then send the image back. That will take another 4 years. So optimistically, if I assume that I will live till 80, you need a spacecraft that moves at 1/5 of the speed of light. And the question is, can we do it? And why do we want to find out? Well, we want to know if there is life on the surface. And that would be possible if Proxima b has an atmosphere. So we can first figure this out. It turns out the planet is sufficiently close to the star so that it's tidally locked. It always has a permanent day side and a permanent night side. It faces the star with the same side at all times, just like the moon relative to the Earth. And the permanent day side is much hotter than the permanent night side. And so just as the planet goes around the star, you don't need to resolve it, but you can measure the light curve because you see different fraction of the illuminated side of the planet as it moves around. So you get a light curve of the planet, and from the light curve you can tell the temperature contrast between the permanent day side and the permanent night side. And so, for example, the James Webb Space Telescope could potentially find out, just from the temperature contrast between the two sides of the planet, whether it has an atmosphere, because an atmosphere will moderate the temperature contrast, or an ocean would moderate the temperature contrast. They will transfer heat between the two sides. My daughter, who is 13 years old, said that if we ever move to that planet, she would like to have 2 houses. One on the permanent night side, where she could sleep, and another one on the permanent sunset strip, separating the day side from the night side, where she could have her vacations. So the image, just imagine a place on a planet where there is sunset forever. That's possible. That may exist on Proxima B. That's where real estate will have the highest value for houses. So my daughter knows her business, I guess. And potentially you could have life also on icy objects, objects that are not next to a star but have a surface ice layer, but underneath the ice you could potentially have liquid water. So coming back to the question that I brought before, can we break the walls of the solar system? Can we exit the solar system and visit the nearest star system, and in particular, Proxima B, and figure out whether there is life there? I mean, we know that Earth is a comfortable place for us, at least for now, but there are various threats. There are internal threats. We could easily produce a self-inflicted wound either by going into a nuclear war or by changing the climate as we are doing. Apparently, we're not intelligent enough to prevent that. In addition, there could be external threats. There could be an asteroid impacting the Earth, or eventually, in less than 1 billion years, the sun would warm up enough to boil off the oceans on Earth. So life will not be possible on Earth. It's interesting to look at scripts that talk about eternity. Eternity has a limit. You know, anything that you find in literature that talks about eternity makes no sense in astrophysics. Everything changes. The sun will die. So here is an interesting thought. Einstein already figured out that if you are in a falling elevator, right, when the elevator falls freely, if someone cuts loose the cord that holds the elevator, you would not feel the force of gravity because your feet will sink at the same rate as the floor. So there will not be any force acting on your legs, and it would feel like there is no gravity. But the same is true in reverse. If you are boarding a spacecraft that is accelerating you at the surface acceleration of Earth, 1g, it would feel just like we feel in this room, even if there is no gravity. So imagine that this auditorium was part of a spacecraft pushing us through space with 1g. It would feel exactly the same as it feels right now. But if you do that for 1 year, if we sit in this spacecraft for 1 year, turns out there is this numerical coincidence that 1g times 1 year is the speed of light. We would reach the speed of light in 1 year. If you sit in this spacecraft for 25 years, you can cross the entire universe. How is that possible? The universe is, it takes light 10 billion years to cross it. Well, it's because of Einstein's theory of special relativity that time is ticking at a different rate if you are approaching the speed of light. So if you could continue to accelerate for 25 years at 1g, you will reach the edge of the universe. That's quite remarkable. We can design a trip to the edge of the universe per galaxies that you look at. The issue is that you need more fuel than the Milky Way as a whole can accommodate. But in principle, it's doable in a human lifetime. Now, trying to be more practical, how can you launch a spacecraft to a fifth of the speed of light? Well, rockets are limited. How does a rocket operate? It basically shoots back gas and gets the momentum pushing it forward. Okay? And the same is about, if you sit in a jet plane, that's the mechanism as well. I once tried to calculate it on the back of an envelope, and the numbers work out as to the amount of fuel that you have to burn to push your jet plane forward. The problem with that is that when you shoot the gas in a rocket, you shoot it at some speed. That's called the exhaust speed, the speed of the gas when it leaves the exhaust. And that limits the speed of the rocket because at most, the rocket can reach that speed times some logarithmic factor related to the amount of fuel that you carry. And the main reason is that you have to carry the fuel with you to start with. So you carry something very heavy, you throw it back, but you cannot gain much more than the speed, the exhaust speed. You can get a factor of 10, maybe more than the exhaust speed for reasonable fuel to payload ratios. So that's why, since Sputnik, all space missions reached roughly 20 to 30 kilometers per second. That's the terminal speed. If you compare New Horizons to Sputnik, it's roughly the same speed. And it's the rocket equation, because these devices carry the fuel with them. So the only way to avoid the rocket equation, the main way, is not to carry the fuel with you. So an example for that is a sail pushed by light. So you are all familiar with sailboats. And let me show you a picture of a sailboat. And there, the wind reflects off the sail of the sailboat and pushes it forward. But if you reflect light off a surface, you also get some push. And the advantage of reflecting light is that you can, in principle, reach the speed of light. You don't have to carry the fuel with you. So we calculated that if you have a laser of 100 gigawatt that shines for a few minutes on a sail roughly the size of a person, then that sail, if it weighs only a gram, can reach a fifth of the speed of light. And this is the amount of power and the amount of time that was needed for the liftoff of the space shuttle. So the only difference is you deliver that power to 1 gram of material instead of the space shuttle. And so this is the concept of Starshot. And this project was initiated when Yuri Milner, an entrepreneur from Silicon Valley, came to my office and asked me if I can recommend a method for reaching a fifth of the speed of light to get to Proxima b. And this was the method we converged on, and it's now a project. And this is a brief illustration of my history, starting from a village, a farm in Israel. That's the year I was born in, and that's the house, which is still there. And I used to collect eggs every afternoon. So I always had plan B. If I didn't get tenure in academia, I would go back to the farm. I still contemplate that possibility when my colleagues make me unhappy. This was a tractor I drove with. I used to drive to the hills of the village and read philosophy books. That's my sister. And at some point, through a convoluted path, even though I was mostly interested in philosophy early on, I ended up in physics and astrophysics. That's my family, by the way, 2 daughters and a wife. And this is Yuri Milner when he came to visit me. And then we announced the project in the presence of Stephen Hawking in 2016. This is Freeman Dyson, if some of you know him. And so let me give you a few details about Starshot. It's under the Breakthrough Foundation initiatives. And the idea is to have this sail, light sail, released above the atmosphere of the Earth, and then a collection, an array of lasers, combining their power to one powerful beam of radiation that is going through the Earth atmosphere and pushing this sail for a few minutes up to a fifth of the speed of light. And that sail carries with it a payload that is the guts of a cell phone that includes a communication device, navigation device, and then it's launched in the direction of Proxima b, and eventually reach. Of course, one has to forecast where Proxima b will be when this spacecraft arrives, and then hopefully it comes close enough to the planet. And hopefully, as well, the planet has some green stuff on it. And then when you take a photograph by a flyby, Eventually, the photograph gets transmitted back to Earth. It takes another 4 years for this light beam to arrive to Earth. And then a big challenge would be to actually receive the information and process it, because the beam will have a spot bigger than the Earth-Sun separation. And Proxima b, just to give you a sense of how precise you need to be, is roughly the angular size of a marble on the moon. Okay, so you need to know where you're heading, and there are many challenges to this project. I'll just mention a few of them. One is to produce the photon engine, this laser beam. Another is to produce a sail that is lightweight but strong, made of material. It turns out that, for example, diamond is a very good material, so you can imagine having a piece of jewelry up there in the sky, like a big diamond sphere of the size of a person, but weighing only a gram, so it's a very thin surface. But you also need to optimize it such that the sail rides in a stable fashion on the beam of light. And one has to avoid damage from impact by dust particles. And then eventually there is a challenge of communication to Earth. And finally, some people tell me that even if you overcome all physical challenges, there is the issue of policy, and convincing people that this device will be used only for peaceful purposes is a major international challenge. And of course, we hope to get to it once we demonstrate the technology. And I'll just skip very quickly and mention the plans for Starshot. In the first decade, we hope to prove the concept, and there is already an investment of funds for that. We have some experimental teams that were assigned the task of research and development. And then in the second decade, there will be a construction of a prototype, and in the third decade, the actual system. Now, you can imagine that perhaps another civilization already developed this technology, and so could we search for the light beams? That's one way of searching for that technology. So, for example, if there is a system that transfers cargoes from an Earth-like planet to a Mars-like planet, you can look for the leakage of radiation outside the sails and search for it. It's most likely that, we usually think about life elsewhere as biological life on the surface of a planet, but it's most likely that biology is just a phase, and eventually you get to technology, like we are currently on a 3-year timescale. Our technology is evolving exponentially, and in the future, it will be technology-based. And so most advanced civilizations might have migrated away from their planet, and we, as humans, are not suitable for surviving in space. People talk about moving to Mars, but that's not realistic because our brain will be exposed to cosmic rays, and 1 in 10 cells in the brain could be damaged in a period of 1 year if you just stay there unprotected. So it's not at all clear that humans are suitable to be away from Earth. What you want to do is send robots with artificial intelligence and 3D printers so that they can reproduce whatever you want out of the raw materials on the target planet. And there may be a lot of interstellar traffic that we are not aware of. And it seems to me that we might as well find evidence for life elsewhere in the form of equipment rather than in the form of biological life. And you can imagine civilizations on journeys sending equipment in some directions, and one such target place could be clusters of galaxies where you have the most fuel for the distant future. The universe is accelerating its expansion. Eventually, it will end up in a very cold state. And so where you want to be is where the party is, where most of the resources are, and that's clusters of galaxies. So it's possible that everyone is migrating towards clusters right now. Now, the mainstream of the astronomy community is focusing on the search for primitive life. And one way to search for it is if you have a planet passing in front of the star, then when the light from the star goes through the atmosphere of the planet, you can get the fingerprints of molecules that are indicative for life, like oxygen, for example, or methane. And there are a number of missions in the future that will be trying to probe the atmospheres of planets. And I illustrate the space missions here. And there will be ground-based missions. So one can search for oxygen, but in principle, one could also search for industrial pollution in the atmospheres of planets. Molecules that cannot be produced naturally. And we calculated that if you get 100 times more than the pollution on Earth, then future telescopes might detect that. And this could be intentional. If the planet is too cold for having life, you can imagine putting a blanket of contamination around it such that it will keep it warm. One can search for the signature of solar cells on the surface of a planet that would reflect light in a different way than rock does or an atmosphere does. And so as the planet moves around the star, you would see, and if it's tidally locked, for example, you can imagine a civilization basically taking the energy from the illuminated side and lighting up the dark side, or redistributing the heat. And that one can look for. You would see that the dark side is not completely dark. And you could see reflectance from these solar cells. Now, most of the community is focused on search for primitive life. In my view, it's important to also allow a fraction of the funds to be spent on the search for intelligent life. And for example, our radio and optical beams can be detected by existing telescopes throughout the Milky Way. But if you look for biological signatures, you are limited to the vicinity of the Earth. Only in the stars nearby, within tens of light years from us, we can have a sensitive enough signal detectable by existing or future telescopes. And technological artifacts, for example, potentially could outlast the civilizations that make them. So you can imagine space archaeology. So just like we dig into the ground by looking for ancient civilizations that are not around anymore, even if civilizations are short-lived, you could search for their relics in space. You could look for megastructures on the surfaces of planets. You can look for burnt-up surfaces as a result of a nuclear war. You can look for all kinds of artifacts, and that would indicate civilizations that are not around anymore, which may be an explanation for Fermi's paradox. And so, in principle, I recommend investing of order a percent or a few percent of the funds that we currently allocate to the search for primitive life towards the search for intelligent life. And that, of course, depends on what's the lifetime of intelligent life. So, about 70 years ago, Enrico Fermi asked a fundamental question. Where is everybody? You know, if there is intelligent life out there, why don't we see evidence for it? And one possible reason is because they have a short lifetime. As soon as a civilization develops technology for us to be able to see them, they also develop the means for their own destruction. And so they have a short lifetime. But then searching for relics would be the way to find evidence for them. As I mentioned before, space archaeology, looking for artifacts. My hope is that if we do find dead civilizations out there, because they changed the climate of their planet or had a war, it would inspire us to get our act together and avoid a similar fate here on Earth. So there is a lesson to be learned from the sky. That we can, in principle, avoid the same future if we behave better. So astronomy serves two important roles in educating us. One, it keeps us modest. Two, it helps us appreciate the value of our planet and the value of being nice to each other. Now, the gold on this ring, the wedding band that I have, came from a source that is quite unusual, and we figured it out only a couple of years ago. It turns out that when two neutron stars collide, a neutron star is just a star weighing roughly the mass of the sun. It's the core of a very massive star that collapses to make a giant nucleus, roughly the size of a city like Oslo. So you have a mass of the sun packed within about 12 kilometers, and that's called a neutron star. And when two such neutron stars collide, there is some neutron matter ejected, and that neutron matter starts decaying, or the neutrons combine to make very heavy atoms, like gold or uranium. So whenever you look at your wedding band, keep in mind that it came from the collision of two neutron stars. And that means that if we were to live, if our civilization happened to be born close to the site where two neutron stars collided, gold would not be worth much because there would be so much of it. So much of it. So the fact that it's expensive is simply because we are relatively far from the nearest site of neutron star merger in our galaxy. And also, if you were to find another civilization, you want to establish contact, you should beware of a civilization born close to the collision site of two neutron stars, because they would have a lot of uranium. So, they might have a lot of nuclear weapons at their disposal. It's just something to keep in mind. Gold and uranium are the sources of evil here on Earth. But molybdenum is actually important for life. Close to the centers of galaxies, there are lots of risks for life because of the black hole in the center. I don't have time to get to the details. In principle, life could be transported across large distances in the universe through stars that move very fast. So one way to get stars moving very fast is when you have two black holes, like we have a black hole at the center of the Milky Way galaxy, and in the center of almost every galaxy. And when two such galaxies merge, like the nearest galaxy to the Milky Way is Andromeda, its sister galaxy, and it's on a collision course with the Milky Way. So when two such galaxies merge, you have two black holes orbiting around each other, and they can eject stars at very high speeds, up to the speed of light, through a slingshot, a gravitational slingshot. And so that's one way of, in principle, ejecting life from a galaxy such that it can move across the cosmos. And, in general, of course, there are also artificial ways of launching spacecrafts to high speeds, as I mentioned, the project Starshot and related projects that other civilizations have. And of course, once we exit the solar system, my hope is that we will get a message back saying, "Welcome to the interstellar club." Now, the interesting question, because there will be a lot of traffic out there, turns out that the very first object that came from outside the solar system, called Oumuamua, was discovered in October 2017. So just a year and a few months ago, about a year and a half ago. And at first, astronomers said, okay, it's coming from outside the solar system. It's probably an asteroid or a comet, just like we have in the solar system. But then it looked very strange. It looked as if it's at least 10 times longer than it is wide, based on the amount of sunlight that was reflected as it tumbled around every 8 hours. So that's at least a factor of a few more than the most extreme shape of a comet or an asteroid that we have found in the solar system. But moreover, it deviated from an orbit expected based on the sun's gravity. And that, in principle, can come from outgassing, from the evaporation of ice on a comet, except that there was no cometary tail sinned. And there are tight limits on carbon-based molecules, CO or CO2. And so question is, what's the nature of this object? Where did it come from? And we cannot, I mean, this particular object is now too far away for us to look at it. We very much hope to look at the next one that comes along, but there is hope also to find members of its family that were trapped in the solar system. If one of these objects passes close enough to Jupiter, it gets deflected in its orbit and could get trapped by the Sun-Jupiter system, which acts as a fishing net and collects some of these objects. And we calculated that about 8 such objects may have already been noticed in existing catalogs of solar system objects. Maybe they are trapped interstellar objects based on the orbit properties that they have. So that would be another way of learning more about the family of objects. And I should just say a few more words about this object, Oumuamua. This is the orbit that it followed, and it passed at the distance which is a fifth of the Earth-Sun separation on September 9th, 2017. We didn't detect it until October 19th, when it was on its way out. This is the orbit of the Earth. And the astronomers were looking at it only for about 5 days in October and then a few days in November because they didn't suspect it to be very unusual. And that was a lost opportunity because it has very strange properties. The most strange of them all is that we didn't expect it to be found. Based on analogies with the solar system, I actually was part of a paper a decade ago trying to forecast how many rocks we should expect that come from interstellar space, and we expected orders of magnitude fewer objects than necessary to explain Oumuamua. It also originated from a very special frame of reference, which is the so-called local standard of rest, which is the frame of reference that you get to when you average over the motions of all the stars in the vicinity of the sun. And it's sort of like a buoy sitting at rest relative to the ocean, and then the solar system ran into it. And only 1 in 500 stars are so much at rest in that frame. And as I said, its brightness changed by at least a factor of 10, a much more extreme shape than one expects from asteroids or comets. And most likely, it's not a cigar-shaped object like most of the artist illustrations on the internet are. It's most likely a pancake-shaped, based on the tumbling motion that it has. If it was kicked around a lot of times, you can explain the light curve that was observed most easily by a pancake shape. And there was no emission, no heat detected from it. So it's very shiny, it reflects sunlight, and small, relatively tens of meters to 100 meters in size. And it deviated from an orbit shaped by the sun's gravity without showing evidence for a cometary tail. And so that extra force that acted on it, its origin is unclear, and we suggested in a paper that maybe it's a light sail that is pushed by the sunlight. And of course, as I mentioned, there are these trapped interstellar objects that one can search for and perhaps study in greater detail. And another possibility is to search for objects passing near the sun, because then the sun would evaporate them, and we could study if there is, if we can study their composition. In a few years, there will be the Large Synoptic Survey Telescope, far more sensitive than the Pan-STARRS telescope that discovered Oumuamua, that will find objects of this class every month or so. But if we don't find objects every month, it means that this one was very unique, and that would make it even weirder than we thought. So let me close with a brief video that was used at the announcement of the project Starshot that illustrates the significance of science and also going into space and exploring our cosmic neighborhood.
We are here. this is home. But for most of our history, we knew only our cradle in the corner. We awakened on this tiny world beneath the blanket of stars, without a note to explain where we come from, who we are. We inhabited a tiny universe, oblivious to the rest of the cosmos. It was only 4 centuries ago that we began to use science to reveal nature's secrets and her laws. What is science? It's an epic journey of discovery. It's a continuity of minds. It's standing on the shoulders of the giants who came before us, looking out across a valley, over a hill, up to the sky, and asking, I wonder what's there.
Oh, that view is tremendous.
It allowed us to look across space and time, see the scale of the universe, and our place in it. We now know that our galaxy alone holds hundreds of billions of stars, and that the visible universe contains at least 100 billion galaxies. In the last decade, we have discovered over 2,000 planets beyond our solar system. It's now estimated that there are tens of billions of habitable planets in our galaxy alone. Are we content to gaze at all these stars, all these worlds, from afar? We have taken to the sky. We have stepped off the Earth. We have walked on the moon. We have landed on planets and comets, and ventured to the edge of deep space. Where now?
Thank you.
Thank you very much for a very fascinating talk. I hope there is room for, well, we have a short time, but a couple of questions I hope we can get. So,
Over there.
there is one over there.
Go ahead.
Just a second.
About nuclear propulsion and how that competes with the pros and cons versus these light sails.
Right.
I think Freeman Dyson was working on this in the 50s or 60s with Project Orion.
Right.
That's my question.
Yes. So Project Orion back then was an ambitious idea that perhaps we can propel a spacecraft using nuclear explosions at the back as the back engine. And they actually, it's interesting, there is the history of this project as described by the son of Freeman Dyson, who is a historian of science and writer. And they used to carry explosives on airplanes to do the testing in some site in California. Nobody cared if they put it in their hand luggage space on the plane. But of course, this concept by itself is not very practical, simply because you know, in terms of the engineering of such a thing, and also nobody would allow you to design a nuclear-based space mission right now because of the risk to Earth. If the launch fails and the nuclear debris falls on Earth, it can cause a lot of problems. But on practical terms, you can think of two nuclear reactors that are not based on nuclear explosions, you know, not nuclear bombs at the bottom of the exhaust. Rather, having a nuclear reactor, either due to fission, using fission or fusion. The problem with fusion, there are many ideas that people have for fusion reactors, but none is practical at the moment. And not only that it's not practical in space, but even on the ground, people are trying to solve the energy problem by having fusion reactors substitute existing energy sources. It's not practical, and then if we demonstrate that we can produce a fusion reactor on the ground, then we can imagine trying to use it for space exploration. But it's always a decade away. I mean, the history of fusion is such that people always promise, in a decade, we might have it working, but it has been already, almost a century. And then with respect to fission reactors, they're simply too heavy. I mean, so you're carrying something very heavy, and you're burning some fuel, but you cannot really boost it to a fraction of the speed of light. With all fusion reactors, at most you can hope for, is a few % of the speed of light, but it's an order of magnitude less than with light sails. So if you're really aiming at reaching a fraction of the speed of light, there is no reasonable alternative. I mean, you can imagine on matter-antimatter annihilation, because then you get pure energy out of your fuel, but we don't know how to trap antimatter in a way that would serve as fuel. You can trap a few atoms in the laboratory, but it's not really practical design. So I would say, as of now, that's the conclusion that we reached. The light sail concept is now is the most practical one. If you are happy with lower speeds, then there are alternative methods. You can have ion propulsion, but if you want to reach a fraction of the speed of light right now, light sails are the only game in town, I would say.
So how does the project Starshot is being funded? I'm asking this because of knowing you mentioned the policy. Everything in the United States, lasts for 4 years or 8 years. So you need to have a long-term kind of funding and a business model for a couple of decades.
Right. So the idea is that the first decade will be dedicated to research and development, and the funding for that at $100 million or so is provided by Yuri Milner right now. And then if that is demonstrated, the next decade should be funded by an order of magnitude more funds. That could still originate mostly from private sources, although not only him, but additional. But then once you get to the next level of the final system, then you need governments to be involved as well. And the hope is that by making it an international collaboration, that the policy issues will be resolved. Hopefully, we will have a team mentality within the project. And that, the final will cost an order of magnitude more than the second phase. So altogether, we are talking about a cost comparable to the biggest science project that we currently have, like CERN, for example.
So right now, if, let's say, you want to explore the solar system, you need to at least, to have a proof of concept and then to come to the place that you can design a spacecraft and send it to a place like Saturn or Pluto, it takes a couple of decades.
Right.
Whereas with the project Starshot, you could do that in a matter of weeks, even at the prototype scale, even at the lower speeds than the fifth of speed of light.
Right.
So do you look into that as a kind of initial stage, because that could boost, looking into the, let's say, Saturn or Jupiter with the Starshot?
Well, this is an excellent question, and not just Jupiter or Saturn, but for example, Oumuamua, we could have easily chased it down. We cannot do it with chemical rockets, it moves too fast, but if we had Starshot, we could have sent a camera in its direction and got better photographs. So definitely, and I think the future is, in space is starting to be shaped by the private sector right now. We see that. It used to be always a national project, but now as the private sector gets into it, because there is so much wealth in the private sector, there is a chance that we will move faster. And that's the hope. NASA, for example, was alarmed when Israel sent this Bereshit spacecraft at a cost of $100 million because it demonstrated that you can send to the moon a mission that costs 10 times less than big bureaucratic systems often charge. And so the private sector changes the landscape. Yeah.
Peter, I think that's the last question we have time for.
Yes.
Thanks. So I noticed in the animation of the breakthrough that the probe turned itself sideways, and I assume, which would be a problem for you also reaching the edge of the observable universe in 25 years. The reason is that space is not empty. So,
right.
But why not just get rid of the sail altogether?
Yeah, this was an artist illustration, and the artist didn't consult with us. But what we imagined is that, in fact, as soon as the launch is over, the sail will fold to just like an umbrella, basically to reduce the cross-sectional area because of the impact of dust particles or the gas along the path. Now, you can show that if you coat the spacecraft by 1 millimeter of protection, that should, in principle, prevent any damage to the electronics behind that coating. The amount of impacts is not too severe if you just have a 1 millimeter thick layer. But as you point out, you don't want a large cross-sectional area because then per amount of mass, you have to increase basically. You're getting much more resistance to the spacecraft and damage to the spacecraft because that scales as the area, the cross-sectional area per unit mass. And so what you want is to minimize the cross-sectional area, and the idea is that it will be more like a needle as it moves towards the target. And that's why the extreme shape of Oumuamua was interesting in a way. But it's interesting also to realize that anything moving so fast at a fraction of the speed of light would not be noticed by our telescopes. Astronomers would think that it must be some cosmic ray moving through or something else because it's so far away from what we expect. And also these spacecrafts that we are trying to design are tiny, they're small, they don't reflect much sunlight. So there could be things flying around that we don't even notice, and that's my point, that there could be equipment out there. We sent out Voyager 1 and Voyager 2 outside the solar system, but we are just at the beginning, and we will send much more stuff out. And if someone else sends stuff out, or if they're trying to spy on us, we have the technology to look for it, to search for it. And this will teach us whether we are the smartest kid on the block or not, if we find any evidence for equipment out there.
Thank you very much. I have a little thing for you to remember the University of Oslo.
Thank you so much. Usually with a box like that, what kids do is shake it to find out what's inside. And by the way, I should tell you that this inspired me, the shaking of a box inspired me to write an essay to Scientific American about what can we learn about the interior of black hole without actually going there. Because if you go into a black hole, you can find your death there. And so the idea was, if you have two black holes that collide, you basically shake them, and you can find what's inside just by listening to the gravitational waves that come out. But it's hard for me to tell, so I'll open it afterwards. Thank you so much.